Hi everyone, today we're going to learn how to use Z3 as a SMT solver. If you remember, last time we learned how to use Z3 as a SAT solver. This means we use only Boolean variables and propositional logic. The input of a SMT solver is a first order logic formula F over background theory T. And in this tutorial we're going to see two different background theories, the theory of uninterpreted functions and also linear integer arithmetic. And as for the SAT case, the solver, if the formula is satisfiable, returns a model. So if your formula, for example, is over linear integer arithmetic, then the model will be a mapping from your integer variables to integer values. And then if f is unsatisfiable, then naturally the solver should return unsat, and it will return unsat. And Z3, the solver you used in the SAT tutorial, is a SMT solver, and even a very powerful SMT solver. So we've been limiting ourselves by using it only in its SAT capability, but in this tutorial we're going to see a little bit more about how to use Z3 for richer theories. In this tutorial we're going to see how to use linear integer arithmetic formulas to encode the job shop problem and solve the job shop problem using Z3 as a SMT solver. And then in a second part we're going to look at how to use uninterpreted functions to solve the seating arrangement problem. So first let's have a look at how we can write linear integer arithmetic formulas in Z3. You can create integer variables using the int constructor. So here the Python variable x is a literal named also x, an integer literal named also x. And then if you create two literals x and y, so x is int x and y is int y, then you can write the formula e1 that is x plus y, or e2 that is x minus y. And you can also write the formula e3 that is 2 times x, but remark that in linear integer arithmetic you can only multiply a variable, here x, by a constant, here 2. And then finally, if you want to create the propositions, you need the comparison operators. And in Z3 you can use any of the comparison operators listed here. So x larger than y, less than, less equal, or different from y, or equal to y. Now we're going to look at the job shop problem, and we're going to see how we can solve the job shop problem by encoding the constraints. So suppose we are given n jobs, and our task is to plan these jobs which are made of different tasks on different machines. You can have a look on Wikipedia, there's a good instruction on the job shop problem. So each job with I from 1 to n is a set of ki tasks. So ji, the job I is ti1 to tiki. And then we have several constraints. So the jobs need to be executed on a set of m machines. So we have some indication of which machine should be handling the task for all the tasks that we have in the jobs. And the constraints are that each task tij has a fixed duration. The tasks in the job need to be executed in order, so ti1 needs to be executed before ti2 in job I. And a machine can only process a single task at a time. So for example, if ti1 and tj1 have to be executed on the same machine, they have to be executed at different times. And finally, a task started has to be processed until its completion. So we have a function that gives us the duration of the tasks, and when a task is started, we have to process the task until it is finished. An input problem, for example, is the following, and you'll see this one in the coding demo as the first example input. In this sample, we have 3 different jobs for each line. And the first job, for example, is composed of 3 tasks. The first task has to be executed on machine 0 and has duration 3. Second task on machine 1 and duration 2. And the final task of the first job has to be executed on machine 2 and has duration 2. For example, here's one solution that is represented graphically, and you can see the first task in blue being executed on the first line, which represents the first machine, and then the first task of the red task is executed just after. So how are we going to encode the problem? We have to provide to design a set of literals, a set of variables, and a set of constraints that encode our problem. And this set of variables has to give us a solution to the problem. If we have a model, so the valuation of the variables, then we can deduce a solution to our original problem. So in this case, we need to be able to say when the tasks start. We can just use as variables the xij that represent the start time of task ij. And then you can construct the whole schedule because you know the duration of the tasks and you know on which machine the tasks have to be executed. Now that we have our set of variables, we're going to look at how we are going to encode the constraints of the problem. So the constraints are a set of formulas in linear integer arithmetic. The first constraint that we're going to add is that the tasks should start at a positive time, so the xij are positive. Formula is that for all I in 1 to n, so for every job, and for all j in 1 to ki, so for every task in the job, xij is larger or equal to 0. And then one of the constraints of the problem is that the tasks in a job I, where I is between 1 and n, should be executed sequentially. So for all j in 1 ki minus 1, so for all tasks from the first to the before last, the start time of the task ij plus its duration, so duration of tij, is less than the start time of the task ij plus 1, so the next task in the job I. And then the tasks on one machine have to be executed sequentially. So we're going to see how we encode this in Python. For this demo, you have a starter file with some code written in it. You can see that we're importing the same packages as last time. Then we have the solve job shop function in which you're going to write most of the code. And then there is the driver code that reads an input file, so in the same format that was presented earlier. And each line of the file is interpreted as one of the jobs. So let's start by going to the solve job shop function and create the set of literals that we want to use. This set of literals is stored in a list where the list represents the list of jobs and each sublist represents the list of tasks. So for each job we enumerate all the jobs, and for each of the tasks in this job, we create first integer literal xij, and we also put the task information just next to it. So the first element of the pair is the literal that represents the start time of the task. And then the second element is a pair where the first element is the machine number of the task and the second element is the duration of the task. Now let's start writing the constraint and the clauses. The first set of constraints that we have is that the start time are positive. So we write that for each job in the list V and for each task in that job, we add a clause that says the first element of the task, which is the start time of the task, is larger or equal than 0. Then the second set of constraints that we want to add is that all tasks in a job have to be executed sequentially. So for each job in V and then for each task from the first to the before last task, we take the start time of this task, so T0 is task 0, and then the duration of this task, so D0 is task 1. We add the clause that says that the start time of this task plus its duration is less than the start time of the next task. Now we need to add the final set of constraints, which say that the tasks on a machine have to be executed sequentially. That means that a machine cannot execute two tasks at the same time. First, let us collect the tasks for each machine. So we have a dictionary M, and for each job in V and for each task in that job, We assign tMachine to be the machine number of that task, and if that key is already in M, then we append that task to the list of tasks corresponding to that machine. Otherwise, we add the key and assign the list of tasks to be just the singleton list containing this task. Now, for each machine, we have the list of tasks that need to be executed on that machine. So you can pause and think on how you need to encode the constraint now. One way to encode a constraint is to say that for any pair of tasks on the same machine, either the first task is executed before the second one, or the second one is executed before the first one. So for each machine and list of tasks in M, and for each combination of two, so for each pair in these tasks, we're going to take the start time of the first task of the pair and its duration, and then the start time of the second task of the pair and its duration. And then we're going to add a clause that says either T0 is before T1 or the opposite. So we add the clause or T0 plus D0 is less than equal T1, or T1 plus D1 less than equal T0. Now we created all the constraints that are necessary to encode the problem. So we can create first a solver S and add all the clauses to that solver, then call the check method, and if it returns sat, then we have a model, so we call the model method of the solver, and we can print that model. Otherwise we print unsat. Can also be interesting to print the last start time of the task, so we initialize M with 0 and then collect the maximum start time of all the tasks. For each job in V and for each task, M is max of M or integer of the model evaluate task 0. Okay, now let's see if it works. So you can see that there's a few test inputs for this exercise, and we're going to use the jobshop-x1 text file, and you can see that it's exactly the text file that was shown earlier. So if we call our script with this text file as input, we get the following model. So you can pause and read and see that, for example, the task of 0 of job 0 is starting at time 0. And we forgot to print the last start time, and so if we print this last start time, we get 15. You can see that if you had to do it manually, you would probably come up with a better schedule. And this is because this solver is only trying to satisfy the constraint and not optimize for anything. But luckily there's a optimize functionality integrated in the Z3 solver, so you can solve for some hard constraint and at the same time optimize for some other constraints. And we're going to see how to use this. Z3 has an optimization solver, so that's a solver you can use instead of the solver that we called earlier. So instead of creating a solver using the solver function, you call the optimize function. So S equals optimize, and then you can add some clauses the same way you added clauses to the normal solver. You can also add some minimization and maximization objective, and that's the optimization part. So the solver, on top of ensuring that all the clauses you added are satisfied, will also try to find a solution such that the objectives you added in minimize or maximize will be either minimized or maximized. And finally, the same way you did before, you can call the check method on the solver, and it will check that the problem is satisfiable. And it will also minimize and maximize the objectives. And the model will return you the model that was a satisfying assignment and also minimizing the objectives. Now we're back in the demo. And remember that our function solve jobshop takes as argument a Boolean optimize. And so if optimize is true, we want to use the optimizing solver. So if optimize, then S equal optimize, Remark then we don't need to change the way we add clauses, we still add them with s.addC. The difference now is that if we're in the optimizing solver, we want to add a minimization objective. In our case, we want to minimize the start time of each of the last tasks of the job. You could think of different minimization objectives, but that's what we are going to write here. Now we can call our script with the O option after the input file, and you can see that it triggers the optimize option. And if we execute it, then you will see that the last start time of the tasks should be lower. In this case, it's 10 instead of 15. Now that we have seen how to use linear integer arithmetic formulas to solve the job shop problem, and on top of this we've seen how to use the optimizing solver, we're going to switch to how to use uninterpreted functions and solving the seating arrangement problem. Now let's look at our second example of the seating arrangement that we're going to solve using uninterpreted functions. So first, uninterpreted functions are just another kind of literal. We saw how to create Boolean literals and how to create integer literals, and now we're just going to see how to create function literals. And in this example, we have f and f2. So f is a function named f that goes from integers, so int sort, to integers. And then f2 is a function from ints to booleans. Then you can write a function application the same way you write function application in Python. So if here we create a literal x, integer literal x, then we can apply f to x, and this gives us another integer. And then we apply f2 to f of x. So this gives us a boolean. So b is a boolean formula. And note that b is a formula, it's not literal. So when we apply a function to a variable, then this gives us a formula. And this is important when you write your constraints. And then in the model, we'll get a partial map from function arguments to their results. So for example, a model of f would be a map from integers to integers. Now let's look at our problem. So finding a seating arrangement. So here's the English definition. At the wedding reception, there are 5 guests, Colin, Emily, Kate, Fred, and Irene, who are not sure where to sit at the dinner table. They ask the bride's mother, who responds. As I remember, Colin is not next to Kate, Emily is not next to Fred or Kate, and neither Kate or Emily are next to Irene. And Fred should sit on Irene's left. As you look at them from the opposite side of the table, can you correctly sit the guests from left to right? So here you need to think about how to model this problem, and first what are the variables you're going to use, the literals. In this case we only need one variable. We're going to use the uninterpreted function pos from guest ID to position. So once we have a model for this function, we have a map from the guest IDs to the position of these guests. So first let's convert our guests to simple integers. So Colin is 0, Emily 1, Kate 2, Fred 3, and Irene 4. And then we're going to translate this English sentence into a formula using the position literal that we have. So as I remember, Colin is not next to Kate. So in our model, we say that the position of Colin, so pos of 0, is different from the position of Kate, so position of 2 plus 1, not next to Kate, so not on the right of Kate. And then position of 0 is different from position of 2 minus 1. So Colin is not next to Kate because it's both not on the left of Kate and both on the right of Kate. And we can replace this by the not next to constraint. So we'll write a function that encode this constraint not next to, and then we have replaced all these parts of the sentence by this constraint. And the last part is that Fred should sit on Irene's left. And in this case, we write this by position of 3 is equal to position of 4 minus 1. So now we have everything we need to start, and we can switch to the demo in Python. We start by importing Z3, and then we're also going to import the combinations function from the itertools package. Then we can create our only literal for this problem, so the position function, which is a function pos from integer to integers. And then, as you've seen in the encoding, we need a not next to constraint. So here we're going to write a not next to function that takes as argument two variables x and y and returns a formula that encodes the constraint that x should not be next to y. First, let's write the constraint that says that x is next to y. So either x, the position of x is equal to the position of y plus 1, or the position of x is equal to the position of y minus 1. And then we return not the formula that represents next to. Now let's write the solve function that is going to solve the problem. Create a solver S, and we're going to add all the constraints to that solver. And the first constraint is that the guests have to sit between 0 and 4. For I in range 5, we add the constraint that says the position of I is larger than 0. And then another constraint that says the position of I is strictly less than 5. We also need to make sure that two different guests cannot be on the same spot. And we express this by saying that for each pair of guests, so for each the combination of range 5, 2, the position of the first guest is different from the position of the second guest. Now let's add all the seating constraints. So the first constraint says that guest 0 is not sitting next to guest 2. And we have 5 of these constraints. The second constraint says that 1 is not next to 3, and then 1 not next to 2, then 2 not next to 4, and then 1 is not next to 4. Finally, we want to ensure that Fred is left of Irene, so we say that the position of 3 is equal to the position of 4 minus 1. And we wrap up by calling the check method of the solver S. If it's satisfiable, we print the model, and if it's not, we print unsat. Let's call the solve method in our script, and then we can run our script. You can see the result here, so the model is a function that maps 1 to 4, 2 to 0, 3 to 1, 4 to 2, and any other integer to 3. And in our case, the only integer that we're interested in is 0. Naturally, in this example, you could have used only linear integer arithmetic and created all the variables that correspond to your guest. But as you can see, there's also an easy way to encode this with an uninterpreted function. So I suggest that as an exercise, you just use linear integer arithmetic and variables for each guest to encode this problem. And it should also be easy to solve.